Thank you very much for the introduction. And first of all, I would also like to thank the organizers for putting this wonderful meeting together. Thank you, and also for the invitation. Let me give you an overview of my talk, and I think I'll try to use the laser pointer over here because then I don't have to walk back and forth between my computer and the slides. But it doesn't work? No, what's happening? Sorry, I think I need to restart. Sorry. No, it works. It was just hanging up. Now it works. Okay, so here's the outline of my talk. As you have seen from the title of my talk, I will mostly concentrate on talking about the sodium-potassium experiment. But at the beginning, I would like to give you a short overview on the second experiment that we are working on in Hannover and what the status of this experiment is. Well, then I'll switch to the sodium-potassium molecules in the low vibration ground state, tell you about our understanding of molecule-molecule and atom-molecule collisions up to the current point, and then tell you about control or our work towards controlling atom-molecule and molecule-molecule collisions. Well, in Hannover, we do have two experiments. One is a direct laser cooling experiment working with calcium fluoride molecules, and the second one is this association experiment of ultra-cold atoms to bialkali molecules, so the sodium-potassium experiment. Well, let me just give you a brief overview of what we are up to with this direct laser cooling experiment of molecules. Well, we are interested mostly there in developing advanced cooling methods for the direct laser cooling of calcium fluoride. Why? Well, there have been really great advances in the last few years on direct laser cooling of molecules. Magneto-optical trapping is nowadays a standard tool. Subdoppler cooling in optical molasses, then all these experiments on laser cooling in optical and magnetic traps, and even in optical lattices, and this beautiful work on optical tweezers. However, at the current point, all these experiments are working in the ultra-cold regime, but the densities of these molecular ensembles are still relatively low, and therefore also the phase-space density being still far away from quantum degeneracy. And one of the critical points is that you start right away from a relatively low density MOT with densities on the order of 10 to the 6 per cubic centimeter, maybe 10 to the 7. But for atoms, you typically have 10 to the 10, 10 to the 11 atoms per cubic centimeter. Well, and why is this? Well, the low density in the magneto-optical trap comes first of all from not so efficient atomic molecular beam slowing techniques at the very beginning, starting with a buffer gas source for the molecules and then implementing some slowing techniques. What's missing here is a CW scheme, which is at the same time a velocity compressing to really have a large number of molecules at velocities which you can actually trap in magneto-optical traps. And then MOTS are notoriously hard for molecules due to the fact that you're working on this J to J equals J minus 1 system. You need to use two optical frequencies to trap those molecules to induce the Doppler cooling force, but this results in start shifts that actually induce subdoppler heating. And on the calcium fluoride experiment, we are thinking about possibilities to improve on both these things. On the one hand, we have come up with a Zeeman slowing proposal, which is actually a Feshbach slower proposal. What's the idea here? Well, instead of implementing a Zeeman slower in the low magnetic field region, where you have Zeeman structure, which is really complicated for the molecules in low magnetic fields, you'll go into a high magnetic field region, where on a typical laser cooling transition, you'll basically split up the ground state and the excited state into spin up, spin down states plus some substructure. And then you'll end up with this 4-level scheme here now with a small g factor in the excited state, which you can approximate by a 3-level system. And then it's easy to implement a Zeeman slowing scheme. How does it work? Well, you have a magnetic field dependent transition from 1 to 2, which can induce such a velocity magnetic field dependent force. And then in addition to this, now you lose, of course, you lose molecules to the 3 state because there's no selection rules preventing the molecules from not going into this 3 state. However, you can apply a broad repumper to pump back everything into the cooling cycle. And then simulating the scheme, you'll get a narrow force profile, which looks like this. So this is force as a function of velocity. It's narrow in velocity space. That's what you need for Zeeman slowing. It's also dependent on the magnetic field. So it moves around when you change the magnetic field. And putting this into a Monte Carlo simulation, you indeed compress the entire velocity distribution from a buffer gas source to a narrow peak at low molecular velocities. But does this really work in the experiment? Well, we can measure force profiles. So this is force as a function of velocity. And as you can see, it's tunable in magnetic field. There are different curves for different magnetic fields. And it's narrow in velocity with a width of approximately 40 meters per second. Putting this into a Monte Carlo simulation, it should still work. And then we do the Zeeman slowing in the experiment and try to get a signal. And there we still face some issues. So here in blue is the velocity distribution of the molecules as it comes out of the buffer gas source. And at the time, the source was relatively hot with a center velocity of around 170 meters per second. Then we apply the Zeeman slowing, and we can push the velocity distribution towards lower velocities. But as you can see, either we produce some hot molecules or they remain behind. And if we go further to 50 meters per second, you see that molecules accumulate at large velocities. We don't really know where this comes from right now. Okay, then we are also thinking about those hot magneto-optical traps, which are, as I said, so hot because of subdoppler heating. And well, molecular mods are typically a millikelvin hot with a size of approximately a centimeter. And I already explained where this comes from this bichromatic magneto-optical trap and Stark shifts pointing in the wrong direction, basically. But we know from optical dipole trapping how we can actually tune the Stark shift while not affecting the scattering by just having a far detuned laser beam. And this would be the idea, to just add an additional low detuned laser beam to push the AC Stark shift into the right direction while not affecting the scattering force, and therefore engineer subdoppler cooling techniques, subdoppler cooling force profiles. And this is a simulation where you see again velocity distribution as a function, force as a function of velocity. This is this initial bichromatic force scheme. And then you see that you can significantly reduce or even flip the subdoppler heating peak into a subdoppler cooling peak by adding this Stark shift tuning. Okay, with this, I'd like to jump over to the bialkali molecule experiment, where we're using sodium and potassium to associate them to sodium-potassium molecules. And in Hannover, we have roughly around 10,000 molecules in the row vibration ground state. Temperature is 250 nanokelvin in a crossed optical dipole trap. And the phase-space density, after we create those molecules without any shielding or anything, is 0.14, so about an order of magnitude away from being quantum degenerate. And this is an expansion image from our releasing the molecules from the optical trap. Well, our experiment is one of those many experiments. We have the spider web almost complete. Maybe I also forgot a molecule. I'm not completely sure. And well, there is already quantum degenerate Fermi gases for those bialkali molecules, but using fermionic molecules. And we are working with the bosonic molecules right now. Let me just briefly tell you how we prepare the molecules, just some experimental details. I mean, the general scheme you all know. It's this 3-step process that we introduced at Schiller at about 2008. In our case, we prepare a dual species quantum gas in an optical dipole trap. We can also go down to dual species quantum degeneracy, although that's not the best spot to actually prepare the molecules, because then you have strong losses for the Feshbach molecules. Then we associate the molecules, the atoms to Feshbach molecules by direct RF association, so from the threshold to the bound state using RF photons. And then we do the stir-up from the triplet ground state to the singlet ground state via some electronically excited state where there's a resonant mixing between a triplet and singlet character in those two potentials. Okay, then just that you know which state we're actually working. Well, those singlet sigma molecules do have hyperfine structure, which comes about due to the different nuclear spins of the atoms projected onto an external magnetic field, for example. And we are working at external magnetic fields because we're using Feshbach resonances. And well, what you then end up with is a manifold of hyperfine states, which is actually just the different projections of the nuclear spin onto an applied external magnetic field. Well, and this is, no, I can't read this. Yeah, over there I can read it better. This is the potassium nuclear spin, and this is the sodium nuclear spin with a larger splitting. And in all these experiments, we work with molecules in the second highest state of the molecular manifold. Okay, as I said, we are still about an order of magnitude away from being quantum degenerate, and with a phase-space density of 0.14. And we are now interested in bridging this one order of magnitude by means of evaporative or sympathetic cooling of the gas. However, as you know, collisions between almost all the bialkali molecules are really nasty and induce strong inelastic losses. And this is not only the case for the chemically reactive molecules, where this exchange reaction is exothermic, one example is potassium rubidium, with which we have worked at Schiller, and where we observed fast two-body loss due to those chemical reactions. This is also the case for the non-reactive molecules, where this chemical reaction is endothermic. Well, this is our experimental system. Here, down here is the sodium-potassium plus sodium-potassium state, and here would be the outgoing state. It's excited by 14 or splitted by 74 wave numbers. Nevertheless, we do observe loss. This is the molecular system as a function of time. Plotted in black is the decay of the pure molecular ensemble, and you should care right now only about those data. And as you can see, it's a decay on a timescale of 100 to 200 milliseconds, corresponding to a two-body decay coefficient of almost 5 times 10 to the minus 10 centimeter to the power of 3 per second, which is close to the universal limit. Well, and almost all those non-chemical reactive molecules have seen these losses in their systems. And the origin of this decay is by now known and widely accepted, but it has been a puzzle for a long time. So what happens is that two molecules approach each other, they sample the long-range potential, they see the tetramer potential, and this tetramer potential supports a huge density of states, leading to the formation of long-lived tetramer complexes with a lifetime, which is still under discussion. And during this lifetime, there will be photo-induced losses, effectively leading to the removal of molecules from the trap. Well, as I said, this photo-induced loss process via tetramer formation is by now widely accepted. What's still a discussion is the lifetime of those tetramers. The first prediction was by Christian and co-workers from RRKM theory using transition state theory and phase integrals. And what they predicted is lifetimes on the order of microseconds. Well, then people went ahead and get an estimate on this lifetime of the tetramers in chopped optical dipole traps. The idea being that those molecules hold in the dark during the chopping time would have the possibility to dissociate again, and you would see an enhanced molecular system. What happened is that some experiments saw more or less an agreement with theory, in particular the rubidium-cesium in one particular spin state, but all the other experiments observed far longer lifetimes of those complexes than predicted from this RRKM theory. And also the trimer, as observed in a potassium rubidium experiment at Harvard, observed much longer lifetimes for the trimers than expected from a simple theory. Well, this is still a matter of discussion, and there have been a large number of theory work discussing the origin of this discrepancy. And well, you have probably seen the poster yesterday, P21, where it has been proposed that field dependence of the sticking time might be at the origin of what we see there. For sodium potassium, they predict lifetimes of those tetramers up to 100 milliseconds, and that's more closer to what we observe in our experiments. So it seems to resolve at some point. Well, nevertheless, we have to live with those strong losses, and we would like to control those collisions to prevent the molecules from undergoing strong losses. And well, we started with this controlling collisions already at Schiller, the idea being to just manipulate the long-range potential between two molecules, introduce a small collisional energy barrier to prevent the molecules from getting close enough to each other to undergo whatever loss mechanism. And at Schiller, we started by investigating the quantum statistics, flipping fermions spin-aligned to spin mixtures, and then observing P-wave versus S-wave collisions. We also put the molecules in, we also induced the dipole moment of the molecules and used confinement in restricted geometry to prevent the molecule, to design potential energy barriers and therefore prevent the molecules from getting close enough to each other to undergo loss. Well, what's currently under discussion, and this has also been discussed in this meeting already, is this blue shielding of collisions, which has been put forward already in the 19th for atomic systems, where the idea was to have two atoms colliding and undergoing loss at short range, shielded from this short range by means of addressed adiabatic energy structure. How do you do this? Well, you have this S plus S threshold. You have an excited S plus 3 threshold. You couple those two thresholds with some additional photon. Well, now you get an adiabatic energy picture and an avoided crossing. Two molecules will come in, or two atoms will come in. They see a repulsive energy barrier and go back up. Well, the disadvantage of this scheme at the time was that you have spontaneous emission for optical photons. So meaning that whenever you use the scheme for shielding, you'll suffer loss from spontaneous emission. However, molecules can now use this scheme on the rotational structure, as we have seen, with implemented on the rotational structure where you have the rotational ground state and the rotational excited state as S and P states, and then basically get the same scheme as down here for the atoms. You have the molecules coming in on the n equals 0 threshold, and they see this repulsive potential due to the coupling to this rotational state of different parity. Well, and you have seen the experiments from different groups around the world. At MPQ, they are working with sodium potassium and do the shielding and then get a quantum degenerate Fermi gas. In Hong Kong, they are shielding sodium rubidium molecules. At Cornell, sodium cesium molecules. And this has been the first experiment working with calcium fluoride at Harvard. Well, we would also like to do shielding, but we cannot do this with microwaves. And that's why we are interested in two-photon optical shielding of collisions, which Maxence already discussed at the beginning of this meeting in more detail. I'm just going quickly through those ideas. So this work is a collaboration with Olivier Douilleux, Maxence Leperc, and our own group in Hannover. What's the idea? Well, the microwave shielding scheme works in such a way that you couple a rotational ground state with some rotationally excited state of different parity, and thereby induce an effective dipolar repulsive barrier between colliding molecules. Well, we're now thinking about photons. You cannot use a single photon due to the fact that you'll suffer from spontaneous emission. But why not using two photons, coupling the ground state via some electronically excited state to a rotationally excited state in a Raman-like transition scheme? Well, this would have a couple of advantages. For example, optical fields are, at least from our point of view, experimentally more flexible, and you don't need to deal with all these coils, antennas, and impedance matching. And well, you can much better control the polarization of those fields. However, when doing this scheme, there's of course a decisive difference between the microwave scheme and the two-photon shielding scheme. For microwaves, you'll couple n equals 0 to n equals 1 states. That means states of different parity, resulting in resonant dipole-dipole interactions, and also this repulsive potential energy barrier. For two-photon shielding, you couple n equals 0 to n equals 2, for example. So two states of the same parity, and the question is then, do you get repulsive interactions in some channel? Well, and this is now the adiabatic energy plot of the adiabatic energies for all those different channels. Here is energy as a function of internuclear distance. And well, down here is the ground state adiabatic potential. Then you have the j equals 0 to j equals 1 potential. So the one that's being used in the shielding using microwaves. And then you have this j equals 0 to j equals 2 threshold, which also shows a repulsive barrier. And where does this come from? Well, it's now not resonant dipole-dipole interactions, but second-order dipole-dipole interactions, basically an effective van der Waals interaction. Okay, and experimentally, this then would look like this. You'll start with two ground state molecules. Here's the rotationally excited combination. Then you'll have an electronically excited state with a strong transition dipole moment, such as, for example, transitions to the A state. And this results in an effective three-level scheme. Now, adiabatically eliminating the excited state, of course, it's an approximation and you need to do the real simulation, but nevertheless, you can then map this onto the microwave scheme and get a scheme for the shielding of molecules using optical fields. And we are currently looking into the spectroscopy of this excited state at 767 nanometers to actually see whether we can implement this scheme or whether there's still some experimental hurdles. Okay, with this, I would like to go over to the atom-molecule collisions. Okay, in our experiment, we can have two different combinations of atoms mixed with our molecules. On the one hand, we can mix sodium with sodium-potassium molecules. On the other hand, we can mix potassium with sodium-potassium molecules. And while in this case, he is chemically reactive, meaning that the incoming channel is higher in energy than the outgoing channel. And this is something maybe that we see in the experiment. So what happens is when we admix sodium to the sodium-potassium molecules, we see that the molecular decay gets far faster. This is those triangles. And analyzing this decay, we'll get, again, a two-body coefficient, which is more or less consistent with the universal limit. However, this is now different for the sodium-potassium plus potassium case. In this case, well, there is only an endoergic chemical reaction, and, well, naively, nothing should happen. Well, in reality, of course, to an atom and a molecule approach each other, they sample the long-range potential and see all those trimer states. And now it depends on the nature of these trimer states, what happens. And, well, in our case, this seems to be a really nice system. That's something that we can see when, first of all, just starting from the mixture that we naturally have in our system when producing molecules, a mixture of potassium with sodium-potassium molecules, potassium in the 1-1 state, we mix a large density of potassium to the molecules and do not observe a change in the decay of the molecules. So in black is the pure molecular decay, in gray is the decay of the molecules, adding potassium on top of it. And as you can see, there's a really low two-body collisional decay coefficient, lower than 10 to the minus 14. We can't really measure it because it's limited by the molecular decay. Well, in any case, it's much lower than the universal laws. And this is actually the case for almost all those potassium spin combinations mixing it with the molecules. So we can assume that there's a relatively low density of states for those trimers, and maybe we can resolve resonances. And this is indeed the case. So this is then atom-molecule Feshbach resonances in this sodium-potassium mixture, in the bosonic sodium-potassium mixture. There's additional experiments from the J-wave palm group working with fermionic sodium-potassium, and in catalyst group working with a triplet lithium potassium system. Well, those pictures here are Feshbach resonances in different channels of in different spin states of potassium, always having the same molecular spin state, this one, the second highest of the molecular manifold. Well, now, of course, you would like to understand this, and this is not so easy. We can start with a very, very simple picture right now, and this would be to just plot the threshold energies to first order given by the potassium hyperfine Zeeman structure, going away to the Feshbach structure. This is, well, the threshold energies, just because there's no magnetic moment of the molecule, so you can approximate it just based on the magnetic moment of the atoms. Well, then you have all those resonances plotted here in this diagram. Now you need to find a bound state that crosses those states at those particular magnetic field positions, and in addition, consider selection rules where you would observe resonances or not. Right now, this doesn't work, so just adding this simple structure, we cannot yet predict new resonances based on the crossing when we fit one of the resonances and assume that it's a resonance of a particular character. But we also still have to do additional measurements, because right now we are just arbitrarily choosing an arbitrary polarization for optical dipole trap, not aligning it with magnetic field, and therefore maybe allowing for additional resonances in the system to happen. Okay, and with this, my time is over. Bara told you about the photo association work, which was motivated by the experimental work, where we would like to do photo association on the sodium-potassium system to learn more about those triplet potentials. And this brings me to the outlook. So yes, we would like to prepare long-lived molecular ensembles to bridge this one order of magnitude towards quantum degeneracy. We're therefore looking into this two-photon shielding scheme. We have observed Feshbach resonances between atoms and molecules. Here's just a sample picture of some of the resonances, and hope that we'll maybe be able to do elastic tuning of elastic collisions as well. And this would be really nice, because then we have a dense bath of potassium that we can evaporatively cool and maybe cool the molecules in this bath of potassium atoms. Well, and all this work brings us closer to investigating, or is already investigating, trimer and tetramer potentials and formations. And well, the long future of this experiment is to do dipole many-body physics in lattices. We'll move the collision work to another experiment at some point. Okay, and with this, I would like to thank our collaborators, Olivier Doulieu, Eberhard Thiemann, and Maxence Leper, and the two PhD students working on the theory, Charbel and Bara, and the experimental team at LUH, and there's also one of the NAK students in the lab, Yule. Yeah, and our funding agencies, and also, of course, we are looking for PhD students and postdocs. Thank you very much for your attention.
Thank you very much, Silke. We have time for questions.
You have shown the hyperfine Hamiltonian, and I have a question regarding this part.
You mean for the molecules?
Yeah, yeah, because this Hamiltonian contains at least two components, and one of them is at least, yeah, this C constant. It should be very small.
It's very small. Yes.
Are you sensitive in your experiment right now to this, or you can just assume that it's just the zero?
For us, it's just Feshbach structure, because we're working at around 200 Gauss, and there the spins are decoupled. But when going to low magnetic field, you would see this. Yes.
Other questions? Perhaps I can ask about the optical shielding, because I'm interested in it. Really, what do you see as the advantages of it over the microwave shielding? Because I think it has the same requirements, right?
Yes, it has the same requirements. Finally, for us, it's advantage because we can, you know, it's much easier for us to control optical fields than microwave fields. That's the advantage.
But it's not dependent on the laser polarization in the same way as microwave.
No. Yes. Yes. But on the other hand, of course, you need to realize those Rabi frequencies. You are sensitive to the same phase noise as in the microwave shielding scheme. So when doing this optical shielding, you need to make sure that your sidebands that you're inducing don't have phase noise, so you derive from a single optical beam.
Are there no other questions? In which case, let's thank Silke again for a great talk.